When you think of the most mysterious things in the universe, you might think of black holes, or dying stars, or maybe even distant galaxies. But something even more enigmatic may be lurking in plain sight all around us. Because today we gone now explain what they are, how we know they exist, and why scientists are still searching for them. We can use this same method to measure the amount of mass inside galaxies. In the middle of a galaxy, there is a bright, dense region called the bulge, which contains mostly stars. It doesn't interact with baryonic matter, the stuff that makes up stars and planets and people. Stars and galaxies orbit the galactic center like planets orbit a star. As a planet gets farther away from its star, its orbit gets wider, then the planet will slow down, because the star's gravity is on strong enough to keep it in a tight orbit. And they found something weird. The majority of the mass in the two colliding galaxy clusters was located in the intergalactic medium. These hypothetical particles are called weakly interacting massive particles, or W. Scientists are currently searching for WIMPs in underground experiments to see if they can find evidence of these mysterious particles. The name's not very inspiring, but they're one of the top candidates for what dark matter could be. But to their surprise, the data showed that the expansion was speeding up. This meant that something was pushing space apart, not just pushing galaxies away from each other, but actually pushing space itself. And that something has been dubbed dark energy. And yet, most of the light bending was coming from within the galaxies themselves. Meanwhile, other scientists are using space telescopes to map out the large-scale structure of the universe to better understand how dark energy is affecting the expansion of the universe. It's kind of like a negative pressure that's causing space to expand faster and faster. Another theory, called the Big Crunch, says that the universe will continue expanding until every galaxy is isolated and dark energy will eventually overcome gravity and rip the universe apart. We don't know much about it, but we do know that it makes up about 2/3 of all the energy in the universe. Meanwhile, dark energy pushes things apart because it's like there's a force pushing all of space apart. It is everywhere, but it doesn't seem to clump together in one place or affect another place. And while we have a lot of evidence for their existence, we still don't know what they are. But that's the fun part of science. There are so many amazing things in our universe that we still have so much to learn. We know it exists because we can see the effects on the large-scale structure of the universe. We can map out how the universe is expanding now and extrapolate backwards to see how it started out and project forward to see how it will evolve in the future. And we can use this to test competing theories of how the universe began and how it will end. This meant that most of the mass in the galaxy cluster was not in the same place as the galaxies. The galaxies themselves had a lot of dark matter, but most of the mass of the galaxy cluster was in this big dark matter halo around it. It's as if the group of friends were surrounded by an even bigger group of invisible friends. When a star is far out in a galaxy, it should be going wide and slow, just like a planet. But as we said before, stars at the edge of galaxies seem to be moving way faster than they should be. In the 1990s, two independent teams of astronomers were studying distant supernova or exploding stars. They were doing this to measure the rate at which the universe was expanding. The universe is constantly expanding, and that expansion rate is known as the Hubble constant. This is important because it tells us how fast galaxies are racing away from us. They're not slowing down as quickly as they should, and that means something must be adding extra gravity to make them go faster. In the same way, astronomers can measure how fast distant galaxies are receding from us by measuring how fast their positions are changing over time. If the recession speed stays the same, the universe is expanding at a constant rate. But if it increases, the universe is accelerating. The extra mass in galaxies is thought to make up 80% of all the mass in the universe. So it's like there's some sort of invisible mass that has a lot of gravity, but we can't actually see or detect it any other way. If we look at a galaxy through a massive cluster of galaxies, we can see that the light coming from the faraway galaxy is bent around the massive cluster. They wanted to see how the collision affected the distribution of mass in the two clusters. Normally, when you see a galaxy cluster, you see a bunch of galaxies gathered together, like a group of friends hanging out. Most of the mass in a galaxy cluster is in the galaxies themselves. But as the galaxies orbit each other, there's also a lot of mass in the intergalactic medium, the stuff between the galaxies. All that mass pulls light toward it and distorts the image of whatever lies behind the cluster. Light travels really fast, but not infinitely fast. It has mass, so it's affected by gravity. When light passes near a massive object, it gets pulled off course. And we can actually use this to learn more about both the massive object and the object whose light is being bent. We can see that the massive object has a lot more mass than we can actually observe. Because more mass means stronger gravity, which means more bending. We can also use this effect to identify dark matter, because we can observe where the light bends, and we can compare that to where the mass is located. There are also spiral-shaped regions, called the arms, that contain gas, dust, and hundreds of billions of stars. And orbiting around the galactic bulge and arms is a massive, invisible halo of stars, all together. These make up a massive sphere of matter that we can observe. And I'm not talking about dark side of the force. I'm talking about dark matter and dark energy. You might have heard these terms thrown around before, but do not worry if you read a bit fuzzy on the details. For example, in our own Milky Way galaxy, stars orbit the galactic center at about 250 kilometers per second. Gravity depends on an object's mass. So the farther away you are from the center of the galaxy, the weaker the gravity from all that mass. Since it's so far away, it feels like the stars at the edge of the galaxy are orbiting a lot faster than they should, given the amount of mass they are far from. Like, if the only thing keeping Earth in orbit around the sun was the sun's gravity, Earth would be going way faster than 250 kilometers per second. In episode 1, we talked about how astronomers measure the mass of objects in space by observing their gravity. But when astronomers study how fast stars move around the edge of galaxies, they find that they're moving way faster than they should be. And the only explanation for this extra speed is that there is some extra mass in the galaxy that we can't see. That's dark matter. Now, we can't directly observe dark matter because we can't see it, but we can observe its effects. First, let's talk about galaxy rotation curves. We can also infer the presence of dark matter by looking at how light bends around massive objects. This is called gravitational length. In 2006, an international team of astronomers used the Hubble Space Telescope to image a collision between two galaxy clusters, nicknamed the Bullet Cluster. By studying the Bullet Cluster, researchers were able to compare where the light was bending to where the galaxies were located. All this evidence for dark matter suggests that it is some sort of exotic particle that doesn't interact with regular matter except through gravity. So now let's shift gears and talk about another mysterious phenomenon, dark energy. It's kind of like if you want to know how fast a friend is walking away from you. You can measure how fast their position is changing as you watch them walk away. In the early days of cosmology, astronomers assumed that the expansion of the universe would slow down over time as gravity did its work, pulling everything back together. Dark energy seems to be a mysterious force inherent to empty space itself. One theory says that the universe began with a big bang and will end in a heat death. So now let's summarize. Dark matter pulls things together because it's like a bunch of invisible mass that has gravity. Scientists continue to search for dark matter by sending detectors deep underground to look for WIMPs, the hypothetical particles that make up dark matter. Unveiling the mysteries of dark matter and dark energy will revolutionize our understanding of fundamental physics. And a huge thank you to all of our viewers for watching and learning with us. Leave us a comment below, and we'll see you next time. If you liked this video, hit like and subscribe.